All right, so the first colligative property we're going to take a look at is vapor pressure lowering. And so what we say here is that solutes lower the vapor pressure of a liquid, right? So if you have a pure liquid, it will have a higher vapor pressure than a solution of the same liquid. So here's just kind of a picture of that. So the kind of hand-wavy explanation for this is that these solute particles in here block the liquid from becoming a gas, but they don't block the gas from becoming a liquid, so you end up with less gas and thus lower vapor pressure. However, the true reason for all of this stuff has to do with entropy, and we'll talk about that later on. Another cool picture here for you. So on the left picture, you see we have a beaker filled with some kind of pure solvent, and on the right side we have a concentrated solution, right? And so the one on the left will have a higher vapor pressure, so more gas, than the one on the right. So after some time, this one will lose more gas than the one on the right, and so the solution on the left will actually have less liquid than that on the right. So pretty cool idea, pretty crazy. And so this is summarized in what's known as Raoult's law. And so what Raoult's law says is that the partial pressure of a gas is equal to the mole fraction of it times the pressure of the pure gas. So it's PA, the partial pressure of gas A, is equal to the mole fraction of A times P star of A. And so the star indicates a pure solvent, right? So this is the vapor pressure of solution A. This is the mole fraction of A. And then this is the pressure of pure A. Right, so when it's pure, the mole fraction is 1, and so the pressure of A is equal to the pure pressure of A. And so we can extend this further to say the pressure of a solution is equal to the sum. This symbol right here means sum of the mole fraction of each component times its pure vapor pressure. And so some compounds will not exhibit a vapor pressure, so those are known as non-volatile substances. So if something is volatile, it means that it easily goes into the gas phase at approximate room temperatures. If it's non-volatile, then it doesn't, right? So non-volatile substance, the vapor pressure is approximately 0. So example, table salt is a non-volatile substance, right? If you leave table salt out on your counter, it'll never disappear. It'll never kind of evaporate away. But water is a volatile substance. So if you leave a cup of water out on your counter and you wait long enough, eventually it'll all evaporate away. So let's take a look at an example of maybe a problem you would see. So it's find the vapor pressure of the solution, or the pressure of this solution. And so you have 50 grams of water, and the pressure of pure water is equal to 3.17 kilopascals. You have 25 grams of ethanol, CH3CH2OH. Its molar mass here is 46.07 grams per mole. And it has a vapor pressure of the pure stuff of 5.95 kilopascals. And then you have 5 grams of sugar, which is C12H22O11. And it has a molar mass of 342.3 grams per mole, and it is non-volatile, right? So you've got water, you've got alcohol, sugar, so it's kind of like wine. You can think of it as that way. And so let's figure out the vapor pressure of this solution. So from our previous equation, we know that the vapor pressure of the solution is going to be the sum of its parts, right? Makes sense. So we know that this P of solution will be equal to the mole fraction of water times the vapor pressure of pure water plus the mole fraction of ethanol times the pressure of pure ethanol plus the mole fraction of sugar times the pure pressure of sugar. However, we said that sugar was a non-volatile substance, and so that means its vapor pressure in the pure form is 0, and so all of this stuff goes to 0. So that's kind of the first trick in these types of problems, is to recognize that non-volatile substances have a vapor pressure of 0. And so next up, we have to kind of think about what we're being asked for. So we need the mole fraction of this stuff, right? If we look at the other stuff, the pure pressure of A, we're given that already, so we can just plug that in there. The pure pressure of ethanol, we're given that right in there, so we can just plug away for that. Really, what we need to find is our mole fractions, right? Remember, X is mole fraction. And so we need to convert all of this stuff to moles. And so at this point in chemistry, you should be very good at converting from grams to mole. It should be very, very simple, very, very quick type of operation. So let me just show you real quick. Water, we have 50 grams. I look up the molar mass. I find it's 18.02 grams per mole. Since grams on top here, grams has to be on the bottom here, so we divide, and 2.77 moles. And then I just repeat for the ethanol and the sugar. Right, so here we have 25 grams. This molar mass is 46.07 grams per mole, for a total of 0.543 moles. You can see even though it's only half the mass, it's way less than half the moles. 5 grams of sugar at 342.3 grams per mole is 0.0146 moles, right? So remember that mole fraction, X of A, is going to be moles of A over total moles. So we want to know our total moles, so what we're going to do here is just sum all of these up. And when you sum up, we get 3.33 moles total. And so now we just need to think about our equation up above here, and we just kind of copy paste this down here. That other part went to 0, so we don't have to worry about that. And now we're just going to plug and chug our way through here. So P of solution will equal to the mole fraction of A, remember, or of water, right? So we have 2.77 moles of water. So 2.77 goes on top over the total moles, which is 3.33. And then we plug in the pure pressure of water, which we got up here is this 3.17 kilopascals. To that, we add our mole fraction of ethanol. So we got 0.543 moles of ethanol over 3.33 total moles times the pure pressure of the ethanol, which is the 5.95 kilopascals. Plug all that in, and you'll see the vapor pressure of the solution is 3.63 kilopascals. So overall, not too bad. A bit tedious in trying to find all these numbers, but the concept really is not too complicated. These colligative properties, although we say they don't matter on the identity of the molecule, that's not actually true. All of this stuff and all the colligative properties are approximations. So they get us pretty close to the right answer, and they're super simple. That's why we use them. But if you really want to know kind of the exact answer, you do have to do some more research. So let me just show you this diagram right here. So on the left here, we have what's called an ideal solution. And so in this ideal solution, basically what we pretend is that these solute-solute and solvent-solvent interactions are just basically non-existent, or that they're exactly the same as the solvent-solvent and solute-solute interactions. But you can see that's not always true. When they're strong or when they're weak, they'll deviate away from kind of Raoult's law here. So again, all of this colligative stuff is just an approximation.